Alright, let's get started. I almost feel like saying welcome back, but you've been here. You haven't been the one traveling. But let's resume. So hopefully everybody had fun. A couple of administrative notes. The homework 1 has been graded. I know it's you've known that for a while. What you probably didn't know were statistics. So the class average was 60 out of a total of 55. So everybody did overwhelmingly well. The class average was 109%, which is perhaps why you experienced what you experienced at the this was how we split the extra credit. So we basically sorted your accuracies on Kaggle, and we actually split you into various groups of, like, we were looking for drops in performances of people roughly achieving the same thing. So that red dot was the TA's entry. So there were 10 extra points for being on this side versus that side. But just top performing entries, we would just give you like a smooth step down function. So nearly everybody got something. Okay. Homework 2. The Kaggle entries look interesting. We haven't done this. Show this. Okay. So there was everybody died, nearly everybody doing the same thing. This was on the public leaderboard, and the private leaderboard, interestingly, were slightly higher. So everybody was 100%. This, I can assure you, never happens in a traditional machine learning problem. So this tells you a little bit about the quality of your implementations, that they were good and bug-free. Also tells you something about your political process. It is so easy to classify Democrats from Republicans based on their voting patterns. So unfortunately, nobody outperformed the DA. I realize that that's theoretically not possible, but those were the fine print terms and conditions, so nobody gets a chocolate this time. But next time, with that. What was interesting, I saw some entries by people. Looks like you guys tried, people tried vanilla grayscale. So was that roughly the order in which you uploaded them? Is that?
Yeah, I think so. Yeah, the bottom one I had formatted it bad, so that was null. But yeah, that was the order that I did it. I tried regular logistic regression. I tried adding regularization, which did nothing. I tried a bunch of different values, had no effect, and then I tried naive Bayes. And I tried some more stuff like locally and compared the Excel files, and they were exactly the same. So I didn't see the point in submitting it.
I see. The interesting thing is that if you actually had 100% on training, then without regularization, your weights would be converging to infinite norms. But we must have gotten lucky. There was probably one or a few points that you were making mistakes on the training data. So regularization didn't matter because that error was preventing. It was not linearly separable, and so you weren't converging to a step function. But your test performance was 100%, just like other people. But okay, so yeah, so I just wanted to point out that this was a particularly easy data set, and everybody did well in terms of that. Yes?
I don't understand how it goes. If we miss one in the public data, how can you get 100% on the
Because it's
total data?
Well, it's 37.
Splitting,
Yeah, there's a test split, and then 30% of the test is used for public leaderboard, and 70% is for the private leaderboard. Any other questions about this? Okay. I should mention homework 3 should be out soon. We've been waiting to cover the material before we go ahead and release it. It will contain it's a binary classification problem. This time it's not images, this was a senator prediction. This time it's on data generated by the Large Hadron Collider, LHC. So you're trying to detect the presence of a rare particle through certain features that physicists measure. It's an existing competition that was running on Kaggle, and we took data from there, and we're giving you a subset which is significantly smaller in scale because we want you to actually implement the SVM yourself. So you will not be calling a standard toolbox. Incidentally, we will give you a QP solver, so you won't be implementing a QP solver, but implementing your own solver for the SVM QP, which we'll talk about today, is not all that difficult. There are simple coordinate descent algorithms, but we'll hand you a QP solver. So you'll implement an SVM solver yourself. Okay. All right. So getting to the elephant in the room. So yeah, the solutions for the midterm are available. They're here. How do you go? What's the any feedback? Would you like this to happen to posterity? Would you not like this to happen to others? Any thoughts on the midterm? Was it? Yes.
I like that you didn't make us do proofs for the regular questions.
Okay.
Those were extra.
Yeah, so thank you. Yeah, I tried to make sure that if you wanted to prove, if you're one of those people where I must prove something today, it's available in extra credit. It was designed to be long. I know I got some feedback from students in my lab. It was designed to be long in the sense that it was designed to push you to try to get it to, you would have to prioritize. It was not designed to be long as in just, here's the thing, if you stare at how to get a bell curve properly, turns out that if you take random variables that are peaked at the edge, which, if you look at that distribution, that's pretty peaked at the max possible points. It helps if you have the means at some nice places. So that was the motivation for a slightly harder than usual material. But in some sense, it doesn't really matter, right? You central aperture. Yes.
Now, my opinion is that for me, with the homework or with the test, it usually takes me a while to understand what the question is asking because I'm coming from a machine learning or computer science background. So that was a struggle for me. I felt like I didn't have enough time to really chew on the question and understand what was going on before I could come up with an intelligent answer.
In terms of notation, did you feel it was dense to just parse the notation and understand the question, or just there were things that we hadn't forced you to think about?
Both.
Okay. So
usually I need to write down some equations and kind of get a feel for it before I can, and then it's clear what the answer is. That process was.
Thanks. So the former, I was trying to make sure that's not notation yet. So I usually try to explain what I'm trying to get to and ask a question in words. The latter, that it's requires some thinking till you actually understand what the question is asking. I'll have to think about that.
So how do extra credits work? So is there any difference between extra credits and normal credits?
Okay.
Because you are counting in total.
So the way this works is, that's an excellent question. The way it works is extra credit can only help you if you do it. It will you doing an extra credit will only help you. It cannot hurt anyone else. So what we're going to do is we're going to look at class averages according to regular credit, and if we curve, which we might do in the end for grading, those will be decided based on regular credit, and then we'll add back your extra credit. So you don't affect the curve by doing extra credit. Does that make sense? So extra credit helps you, doesn't hurt anyone else. Any other questions? Okay, excellent. So the solutions are here. Pick them up on your way out. If you have any other feedback, feel free to send me an email. All right, so so I went through Bert's lecture. This was the G20 protest that happened in Pittsburgh. I wasn't physically there. I was away on an internship, but a whole bunch of machine learning students went out and just randomly started protesting with different signs. So this one was support vector machines. And then they had They had Bayesians against discrimination. End duality gap, free variables, and genetic algorithm. That one I support. That one I fully support. There's no such thing as a genetic algorithm. There's a genetic hack. Repeal power laws, as in the power distribution laws. And they actually went out and started marching with people. some people had real signs. Pittsburgh welcomes protesting, like safe for data mining. That was
Heavy.
But so, I mean, some people were trying to say no G20, and these guys were in with their power wars. They actually were featured on The Daily Show for like a brief second. John Oliver was reporting patients against this. So the end duality gap is something that will make sense by the end of today's lecture. Okay. Alright, so let's look at where we were. So last time we were talking about this idea of we had started SVMs. Bert had started SVMs, and it's important to sort of, now that you've seen SVMs a bit, it's important to step back and look at what's gained and what's lost. We want to do classification. We've been doing classification this whole time. We'd argued about, okay, there's two families of methods, generative and discriminative. Generative methods estimate P of x given y, P of y. It's a probabilistic argument. You estimate that, you use Bayes' rule, you get P of y given x, you make a prediction. Discriminative approaches say, let's just estimate P of y given x directly. And this is still a probabilistic discriminative approach. This abandons probability altogether and says, why don't we just learn a scoring function? And I'm just going to round based on that scoring function. There's a philosophy underneath this trend. And the philosophy is, don't solve a harder intermediate problem towards your end goal. If all you care about is classification, then model a classifier and just minimize the error made by that classifier. Right? If you really don't care about probabilities, don't try to learn a probability function. If you really don't care about generating samples, don't care about y given x. Right? So you gain something here, you get a more direct approach to what you're trying to get to, but you also lose something. And along each of these things, you lose something. So when you let go of a generative approach, you can no longer create new data. When you let go of a probabilistic model, you lose calibration. Your model gives you a number back. That number doesn't mean anything anymore. Right? Your model says score of 25.7. That number doesn't mean anything, and not just because it is not between 0 and 1. It is because that number truly does not reflect a confidence. Even if you scaled it by 100 or the max value, a number that is scaled to something that is closer to 1 does not indicate an underlying confidence closer to probability 1. And we'll think about that in a little bit as well. Right? You lose calibration. So when two different classifiers are trained on two different data sets, one of them says 25.1, the other one says 25.2, you really don't know which one is more confident because you cannot use that number. It's not probabilities. That makes sense? Okay. So let's start where we were with SVM. So the underlying philosophy is you want to learn a linear classifier. You want this linear classifier to work well. And work well means it needs to work well on training data and head-off data. On training data, we know that there are many different lines that all give you 100% classification accuracy. Right? There's this line and everything else in between gives you 100% training classification accuracy. The argument that's used is let's use the one with the largest margin. Right? And last time what Bert did was he derived that the margin is actually this quantity, right? It's 2 over the norm of W. And you should, at this point of time, ask, why is, margin is intuitive, but why margin? Why are we trying to maximize margin? A couple of different reasons. A, it's intuitive. B, it's going to, there's some nice theory that shows maximizing the margin for a linear classifier, for example, minimizes the upper bound on the difference between training and test error that you do. Right? So there is something called a generalization error that we have not yet derived formally. I've been appealing to it that something works well on training data, how well is it going to work on test data? But there are these things called generalization bounds where you prove that if I get 25% training error, what is the worst that I could do on test data with some probability? And turns out that maximizing the margin gives you a tight bound. So that's a good thing to do. So there is some theoretical basis for this. Okay. And the other thing is that this idea of margin can be arrived at from so many different kinds of arguments that it's one of those mathematical things that it is so natural, that it has been discovered so many times that there must be some fundamental property. Okay. Alright, so we know that that's fine. Yeah. So we know that margin is 2 over norm of W. One quick note, you may have noticed that in transitioning from logistic regression to SPMs, notationally we made a couple of changes. One was that now we seem to write a W transpose X plus B, the bias, explicitly, as opposed to using homogeneous coordinates and putting a 1 bias feature in X. And the other is why the classes seem to be plus 1, minus 1, as opposed to 0. That's just, those are convenient choices. And those are choices made because, for example, this choice of writing this out separately is made because later on we're going to have to treat this variable separately. So it makes sense. And the choice for plus 1, minus 1 is also mathematical convenience. Like you'll see that, for example, one question in your midterm asked that if you multiply score by y, you want it to be large or small. Can't do that with 0 and 1. Helps if it has a positive sign or negative sign. So it's just notational convenience and it'll match. Different communities have come up with these algorithms themselves, and whenever you pick one of these papers, you'll realize that it was written by someone familiar with a particular community, and there's different notations. So it doesn't really matter, but we're using the sort of canonical notation for every single thing. Okay, so we want to maximize margin subject to the constraint that you get 100% accuracy on training data, which means you correctly classify, you put all the positive points on this side, you put all the negative points on that side. We're not going to, maximizing 2 over norm is a difficult problem, blah, blah, blah. So, like, the thing that's often done is you write norm squared. First of all, you minimize norm squared. That's maximizing versus minimizing arg is equivalent, but you do norm squared instead of norm. And the other thing that Bert may not have mentioned is why did we switch from greater than 0 to greater than 1? Any ideas?
Here we are, this is the score which we discussed, right? It's y into the value which we are getting.
But greater than 0 would have worked as well, right? So I could have said yi times w transpose xi plus b. I could have said just make it greater than 0.
There's no margin.
No, there's no margin in that. Yeah, in a sense, but more precisely, if you stare at this optimization problem, what might happen is you find a w, if this is really 0, right? If this is 0, you find a w and b that work, that get 100% classification, and then you just keep dividing w and b by some constant. You're measuring the norm, and so your objective function keeps going down. So basically, you'll run into numerical problems as well, because your w and b vector, so for example, w, let's say, is 1, 1 or something, and this bias is also 1, right? And that, let's say, works for 0, that it actually does place, it assigns positive score to the positive classes, it assigns negative score to the negative classes. Now you divide w by 100 and b by 100, that'll still work. Reduces the norm of w. Divide w by another 1,000, it'll continue to work. So basically, you'll run into this ill precision regime where your w is trying to just reach to a 0 vector as long as it maintains a particular direction. Does that make sense? And so this gives it a sense of margin. It basically says that you have a line. It's not just that you must place all points here and all points here. It's that they must be separated by some epsilon which can be any quantity, and so might as well choose 1, right? Because these are scale-free quantities. So that's what gives it a scale. And that's why this is W transpose X plus B equals 0, this is W transpose X plus B equals +1, this is W transpose X plus B equals -1. Right? So this essentially prevents your feature space from collapsing to a 0 scale free one. Does that make sense? Okay. So this will be the margin that we're concerned with. And one of the things that we talked about is there will be some points that will be exactly on the margin, which means they will be assigned a score of exactly +1. Right? Those will be what we'll call support vectors, and we'll talk about special properties of support vectors.
Then what are margin vectors? So that's converge with
Well, let's get to the soft margin thing and then we'll talk about that. Okay. So we know how to. Now that we've written that down, let's derive the margin. We've written that down. Okay. This is an extremely well-studied problem. This is a quadratic program. So the optimization variables are W and B. This is linear in W and B. Right? X and so if you pick up a book, it's important to make this mental change that anytime people describe optimization in books, the optimization variable is X. So they'll write min of X, f of X or something, right? Here we're also using X, but X is input to your problem. X is fixed, your optimization variable is W and B. Right? And so you should think of this as f of W. This is the objective function and these are the constraints. So this is all linear in W and B, and the objective function is quadratic, W transpose. It's also convex. It's convex because identity matrix. Excellent. Actually, it's slightly different than an identity matrix. It's actually identity, 0 vector, 0 vector, not 0 scalar, 0 scalar, 0 scalar. Because you actually have D plus 1 variables. D plus 1. Because the objective is quadratic in W and doesn't actually show anything in B. Right? So if you actually wrote down, so this matrix, W transpose B transpose, and W. Right? That's the objective function. That makes sense? So W transpose identity transpose W, W transpose 0, 0, so everything else is cancelling out. There's no quadratic terms in the other things. That makes sense? This vector matrix vector product is that objective function. Okay. And this matrix is positive semi-definite. It's not positive definite, but it's positive semi-definite. And that's fine. That's all we need for convexity. Okay. So the number of variables in this optimization problem are D plus 1. The number of constraints are n. And you can solve this with standard solvers. Okay. And there'll be an interesting, we will prove this, that hyperplane will be defined by support vectors. And this is something that requires a notion of duality that we'll get to. Okay. Any questions so far? Okay. So let's talk about the thing that you guys talked about last time. What if the data is not linearly separable? Right? So far, there was a constraint that said, that get 100% on training data. You separate the training data. If the data is not linearly separable, the QP solver comes back and says there is no W and B that satisfies this. Your QP is infeasible. You have no solution. And so what you'd like to do is you'd like to change your objective function to give you something back that makes the fewest mistakes. And I'd like to do that with, before we jump into Hinge, because I'd like to do that with on the board with Slack. So here's what we're going to do. This is a constraint, so yi times W transpose xi plus b greater than or equal to 1. This has no solution because there is no hyperplane that can put all positives on one side, all negatives on the other side. Right? But what you can do is, this constraint cannot be satisfied, so let's allow some violations in this constraint. And remember, this is not a single constraint. There's n of these, right? One for every data point. And how do you allow violation for this point? Left hand side has to be greater than right hand side. So let's not force it to be greater than right hand side. Let's force it to be greater than some number less than 1. Right? So this is a really common trick in any of these optimization problems where you need satisfaction of constraints, and not all constraints can be satisfied. This is called a slack variable. It's called a slack variable, and this is often referred to as violation of the constraint. Geometrically, this has this intuition. You had some points, positives here, negatives here. What you wanted was, so this is W transpose X plus B equals 0. This is W transpose X plus B equals plus 1. This is W transpose X plus B equals minus 1. You wanted every single positive to be greater than the plus 1 margin. Every time it violates that, so every time this thing scores less than 1, which means greater than 1 minus some positive number, right? So every time it crosses this margin, let's say this lies here. So this is a violation. You actually measure this distance. You measure this distance, and this distance is the slack. There could be a negative sitting here, there could be a negative sitting here, and for those also, you measure the slack, and so that's right. So for a negative, slack is measured from here, because it needs to be beyond the negative margin. For a positive, slack is measured from here, because it needs to be beyond the positive margin. So you're basically allowing these points to violate your margins and lie on the wrong. So remember, this is still correctly classified. It's still on the correct side of the decision boundary, but it's beyond the margin where it's supposed to be. So the constraint is not satisfied. The hard constraint is not satisfied because it's beyond the margin, but it's still correctly classified. Does that make sense? So this is fine, but this also suggests that you have to penalize the violations, otherwise everything can be satisfied, right? I'll just draw a line anywhere and just measure all the mistakes. So somehow we have to allow, so you change the objective function, you say min of W comma B slash I of W transpose W plus C times summation of slacks I equal to when subject to those constraints. Does that make sense? So violations are allowed, but every time you violate a constraint, that adds to your objective function, and we're trying to minimize, so that costs you. So it costs you proportional to some constant C. That make sense? Yes?
Does that slack variable have to be
Positive. Yeah. It has to be positive. Because otherwise, you could start shrinking your margin, and all the things that are positive, all the things that are negative, you start contributing. So if these were negative numbers, then large negative numbers are good for you, and so you'd start doing those sort of tricks. So you don't get any reward. You don't get any reward for satisfying this constraint, right? You only get a penalty if you don't satisfy this constraint.
Does it also have to be smaller than 1, or like if the slack variable is bigger than 1?
No, the slack variable. So think about, so here slack variable is 0. Think about the positive point. When it reaches here, slack reaches 1, because this violation is 1. Here it's 2, and so on, right? So you can put a positive point here. That's fine. So a single positive point will have a large slack, but everything else will be fine.
Where is the vowel to come from?
Oh, so this is an extremely common trick. The half comes, so the half doesn't really matter, right? Odd mins don't change by halves. You write a half because soon we'll start taking derivatives and things will cancel out. So it's mathematical convenience. Like, we're lazy and we like things, don't you remember high school? It's so nice to cut things out. Like, this is just that. It would be nice to cancel things out. Yes?
So So one more question with the matrix,
Yeah.
matrices you wrote, that's just another way of writing the objective function?
Yes. So that was just, so if this did not exist, if you just think of this was W transpose W, which is the same thing as W transpose identity times W. But what I'm trying to do is I'm trying to write it in terms of both W and V, because those were the optimization variables.
Okay.
So this was the matrix that expresses, this matrix product expressed this, because when we were doing the hard margin SPM.
Okay.
This, by the way, is known as the soft margin SPM. It's called a soft margin because the margin can be violated. Just intuitive. Does that make sense? Yes?
Isn't the violation should be slack variable divided by normal?
Should the violation be slack variable?
Distance.
Oh, the distance. Yeah, I think you're right. Because that's why the margin was 2 over norm, right? Yeah. Yeah, you're right.
Still be minimize only the slack variable.
Still be only minimized because the norm is being minimized anyway, and you're not concerned about you're not concerned about any scalar factors because that will be controlled by C anyway. You're just concerned by relative, like how much slacks are.
What is scalar? Norm of W is
You're not really concerned because norm of W is being controlled by this term, right? So for any particular W value, you're only concerned by what is the sum of these slacks. What are the violations, right?
but if we're trying to minimize the distance, like the violation will be psi divided by norm of W, right?
So you're thinking geometrically. If I think algebraically, I wanted this constraint to be satisfied. By choosing this to be 1, I have already made these, everything, I've already fixed a scale to the problem, and now I just need to work with that scale. Right? So if I think algebraically with respect to these constraints, I just need some number here, and I need that number to be small. Any other questions? Yes.
That is the distance of the misclassified one, right?
No, what they're talking about is if you think about geometrically the distance, I think there'll be I may be wrong here, but I'm pretty sure their intuition is correct. I'll have to sit down and write it out. That it'll be z divided by norm of w.
Mm-hmm.
That'll be the distance. It was the same reason why this margin was 2 over norm of w. Okay, so every time we write a trade-off type optimization, it's good to sort of check the extremes. What happens if you set C to 0? No penalty. But what does that mean?
If it's not separable, we can find a solution.
If it's not separable, we can find a solution. So remember, the important but subtle change I made here is the number of variables, the optimization variables are W, B, and the XIs. So the number of optimization variables are D plus 1 plus N, right? There's that many optimization variables. You don't care about this anymore. The only thing that, if you set C equals 0, the only thing you care about norm, I can always satisfy this constraint, right, by making the violations large. And you don't care about the violations. So what do we? So basically, you get a pathological solution. I can set W to 0, and that would be fine.
Yeah.
Right. So if you think about W to 0, that's the smallest norm. You can set V to anything, and set the slacks to make up for whatever it takes to satisfy these constraints, and that would be fine. That would be a perfectly valid solution. So that would be in the extreme case. If you think about priors versus likelihood, the arguments that we were doing, this is you converging to an extremely hard prior. You're just saying 0. Just use the constant, assign everything a score of 0. Does that make sense? By the way, the fact that this is beginning to resemble norm plus something is something that we will exploit. We will soon make that connection precise. Because if you think about logistic regression, naive Bayes, everything that you've done, there was usually a loss term and there was usually a norm term, which was the regularizer, which corresponded to a prior by exponentiating the negative of the norm. Right? We'll make that connection precise. Okay, what happens if you set C to infinity? The other extreme? Come on.
Get a hard margin.
It's like very small, a zero margin.
It would become a hard margin SVM because violations are no longer tolerated, right? Infinite penalty. If you make any violation, suddenly your objective function value goes to infinity. So violations are not tolerated. So basically, you can shrink your norm. You can shrink your margin, which corresponds to increasing your norm arbitrarily, but you will not tolerate any violations. Right? And so, if you actually did have non-separable data, your objective function will return back infinity. Can't be done. So, okay. Does that make sense? Okay. So now the connection that I'd like to do is I'd like to make this. So this is a constrained QP, right? There are that many variables, d plus 1 plus n. There are that many constraints. N of those, n of these, 2n constraints. Right? So this is just a slightly larger. This is still quadratic in W. This is linear in Z's, right? The constraints are still linear. So this is W transpose Xi, so it's linear in W, it's linear in B, it's linear in Zi. So these are still linear inequality constraints, right? Standard QP solvers will solve it. And in fact, in homework 3, that's what you're doing. You will have to convert this sort of a problem into sort of a matrix format that can be fed into a QP solver. Does that make sense? Okay. Now what I'm going to try to do is I'm going to take this constrained QP formulation and I'm going to write it as an unconstrained quadratic problem. So let me try to do that. So here's one thing to notice. We know that this Zi is positive, and let me just rewrite terms to get another lower bound on Zi. Right? So it's also that Zi is greater than or equal to 1 minus yi W transpose Xi plus B. Okay? I've just swapped some terms. This is a lower bound in Zi, this is another lower bound in Zi, so I can combine them together by saying Zi must be greater than or equal to max of the two lower bounds. Right? Max of 0, comma this term. Okay? And in fact, I'm going to make an even bolder claim. And the claim is, this is a minimization problem, right? So let's say the argmin is equal to W star, B star, Zi star. Now let's say that's the argmin. The claim I'm going to make is that at optimality, which means Zi star, is actually equal to the max of 0, 1 minus yi W star. Transpose So you get what I did? So all I said was there is some optimal solution. At optimality, it's not the case that this is greater than or equal to, it's actually, it's never strictly greater than, it is actually equal to this. That seems reasonable?
We're trying to find the minimum.
Exactly.
So
if you stare at this, you're trying to minimize each one of these terms. You know it must be greater than something. You have to hit that. You have to hit that lower bound. If you don't hit it, I could always show that this is actually not the optimum, that you could reduce this objective function. And the proof is in the notes. It's actually just what I said, I wrote down. Does that make sense? Okay, so this has to be true. At optimality, this has to be true. So if at optimality you know that there is some relationship between this one variable and these other variables, you can actually encode that relationship and write it in the objective function. And this is a really common trick. And so what we can do is so this was constrained QP. And I can actually write an unconstrained QP, which is min of W comma B of half W transpose W plus something that I'm calling, let me just write it out, then plus max of 0, 1 minus what's this? yi plus summation ci to 1 and blah 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 yi double transpose xi. Let me finish this one and then I'll stop. This seems like a really ugly notation. Like, what is this? Why does a min have a max sitting inside it? Don't think of it like that. Just think of this as some function called the hinge function. It's a hinge function of yi double transpose xi plus. A hinge function is a really simple function. It looks like this. This is 1, 1, and a hinge function looks like this. H of z equals max of 0, 1 minus. Why is that? This is the z equals 0 part, and this is the 1 minus z part. It's a straight line, and you're taking max, so at every point it takes the larger value. It is just some function. It's not differentiable at this point, but it's just 2 lines, right? There's not much to this function. And what I'm saying is take that function and minimize that function with this argument. And this does not require any constraints because all the constraints have already been absorbed into the definition of zi. Does that make sense? This is actually, this part doesn't even relate to, like, this is extremely important to machine learning, but this trick of converting a constrained optimization problem into an unconstrained optimization problem by adding some functions that have some non-differentiability is really it's a common trick. Okay, so this is known as a hinge loss or a function. The reason why we call it a loss is because pretty soon we're going to relate this. This is already beginning to look like something. This is the regularization, and this is the loss part. Remember, in most algorithms that you've seen so far, linear regression, naive-based logistic regression, there's always some loss, squared loss, or argmax of log probability, which is argmin of negative log probability, plus some regularization. Right? This is turning into that. Does that make sense? Okay. I need to make a connection precise. Let me show a slide and then I'll stop. So this is important to show. Okay, so this is the important part. On your left is an SVM. We wrote down the QP. We reached this optimization problem by arguing about margins, by linear separability, and then we did some math and we converted it into minimization of norm plus a function that looks like this hinge. If you think about a logistic regression, what do? You write down probability of y given x, and then you log likelihood, right? Think about a positive data point for now. Don't worry about a data set. There's a single positive data point. This is its log probability. You want to maximize the log probability, it is the same as minimizing negative log probability, which is this function, log of 1 plus e to the blah blah. Right? If I draw that function, it looks like this. Right? So we're minimizing this negative log probability plus some regularization. The regularization is actually identical. So all of that work, all of this argument, go for something direct, geometry, margins, comes down to a difference between these, right? Whether you do a straight line that drops to 0 or whether you do this function that smoothly goes to 0. Right? But this matters. This makes a big difference. And it matters because if you stare, this is what Bert was trying to tell you, if you stare at that function, the log loss does not go to 0. It is approaching 0, but it never goes to 0. More importantly, its gradient doesn't go to 0 either. The gradient is always positive. It is 0 at infinity, which means no matter how much progress you make, there is still more you can do. It's kind of like Indian parents, right? No matter how good you get, there's more you can do. At least how I view Indian parents. This one is much nicer. Make some progress, all right, you're done. After this point, there are no more gradients, there's no more improvements that you can make to the objective function, and this fact that it actually becomes equal to 0 is going to lead to sparse solutions. And that's going to be important. Sparse solutions mean that our weight vector is going to depend on a sparse number of training data points. That we're going to express a weight vector as a linear combination of data points, and that linear combination is going to be sparse. You won't be able to do that with a logistic regression. It's going to depend on every single training data point. You change every single training data point, and it's going to make a difference to the weight vector because the gradient doesn't die away. Does that make sense? Okay.
So instead of a hinge, if we had something like this, that means we're pushing the positive points more in the positive region?
See that one more time?
If instead of the hinge function, we had something like the blue one,
Yeah.
suppose, then does that mean we're pushing the positive points more in the positive region?
Yeah. Yeah, exactly. So the weight vector, like right now, so what's on the x-axis, actually what you're asking. The x-axis is the score that you've assigned, right? To, let's make life simple, just one positive point. The score that you have assigned, you want to assign as high a score possible. The logistic says keep going, keep assigning a higher score. It's just never going to 0. The hinge says as soon as you've assigned the positive to a score of +1, after that you're done. Because then you're beyond the margin. And then you don't care. And that's why that number, whether it's +1 or +200, doesn't actually tell you about confidence. Right? Okay, let's take a couple of minutes.
这的 x y 轴分别是这的 x 轴和 y 轴。
There you go. Oh, thank you.
等等的 x 轴是，对啊 ，x 轴是多少？
X 轴是它偏离的真相。
y 呢
？y 是 loss。并不 loss 就是你只要准 loss， 不准 loss 就是线上的。所以这个就是你就算是准的，它有 loss。因为 logistic 它建立是个概率模型，如果你离那个分界点太近的话，它给你算的是最大的。所以这还是有 loss。就算你是个好的人，可能你最开始你是有 loss 的。 如果你只画一个定制 loss 的话，它是没有，它自己画出来的。所以它管这个一拿这个叫没事。
这横轴就是算出来这个数嘛，就是 discriminative 的那个。隔离有多近嘛？就是你要算多大一嘛，越大于越好。
但它其实并不是越大于越好，只要大于就够了。 说的对，那时候可以做调整 C 来很准的这个样子。你们说的都对。其实我们是调整的之前，跟这个比较像的。
肯定是。怎么看怎么怪。
其实他们就是直接画一个线就是。他们先把我们写的那个验出来，然后再随便拽条件上去。你要所有的拿一下，我看。 现在看到
Okay. Let's let's get started. So I got a couple of questions, so let me do this one more time. There seems to be some confusion. So this is your optimization problem. This is a soft margin estimate. If C is set to 0, think of C as a trade-off parameter between how much you want to minimizing the norm equals maximizing or is equivalent to maximizing the margin, right? And C is penalty on slacks. High value of C means you penalize violations much more. You care about violation, you care about perfect separation much more than the size of the margin. So when you set C to infinity, you will not tolerate any violations in the margin, and therefore what you will result in, yeah, so when you set C to so this is linearly separable data. When you set C to infinity, if it is linearly separable, you basically converge to a hard margin SVM, right? You are no longer tolerating any violations in this margin. So it will try to do whatever best it can subject to the hard margin constraint. When you set C to 0 in the next, so actually this is great. If you set C to 0, this is what the optimization problem looks like, right? So you essentially convert.
But there is a 1 minus epsilon.
Right, exactly. There's a 1 minus, thank you. I was confused. What is going on? There's a 1 minus epsilon, and so that can always be satisfied, right? I can always construct any W. This is a nice W, right? But I can construct any W, and it's going to make certain mistakes, but you don't care about the mistakes. And since the objective function only cares about the norm, I have to just set the norm to 0 to be done. Okay. All right, so that's good. So we've made this connection. What I want to do next is I want to go to this topic, and Bert started this topic, but we want to get into a little more details of this. This idea that linear separability is linear in what? Linear in some space. Okay. Just because things are not linearly separable now does not mean you cannot make them linearly separable in some other space. And this is the intuition here, right? I just have to add another coordinate, and this now becomes linearly separable. This data was not linearly separable, it is linearly separable in this new space, right? So obviously what you can do is hand design these extra dimensions, feed it into a linear SVM, and be done with it, right? And hope for linear separability. What we are going to go do next is study something known as the dual optimization problem to an SVM. And what that will expose is a particular kind of structure. And in that dual, you'll be able to you won't have to hand design these. So this is, for example, called a feature map, right? You've taken an input, and this is phi. We've studied this before. So you will not have to hand design phi. You'll still need to hand design something that'll just be something called a curve. Does that make sense? Okay. Last time we looked at, by the time this always works. So actually, you can have, if you go to a high enough dimension space, you can always achieve linear separability. And there was this intuition that if you take every data point and make it into its own coordinate, right? So 2,000 data points, 2,000 coordinates for one, wherever that data point, you have linear separability. Right? I can always set W for that coordinate to be +1 and everything else is there. And this type of a theorem should scare you. This is not a good theorem. A theorem that says, I have a classifier that can learn anything, that's a really bad situation. Because it can learn that, which means in order for you to distinguish that from whatever you're trying to teach it, you're going to need a lot of data till it figures out that that's not the concept you wanted to learn. The fact that it can learn a lot of concepts means that it's going to need a lot of data till you nail down uncertainty into a region which corresponds to something sensitive. Does that make sense? Yes?
I was wondering, like you said, the only difference between the logistic and the Hinge is just the shape of that.
Yeah.
So are those both specific instances of more general classifier with like any arbitrary shape you can make up?
So you can start defining arbitrary loss functions, and this idea of loss plus regularizer, where loss has some behavior or shape that you like, you can define your new models that way. And you can write down an objective function, minimize it to do something. That's not the reason why those classifiers are interesting.
there's sort of an argument that led to this shape, and what's interesting are those arguments, right? Here, it's a probabilistic model. After you've learned W, it gives you a probability. Here, it's a max margin classifier. I haven't taught you the theory, but it gives you an upper bound on generalization error. You write some other shape, what does it mean? Right? So if I'm, for example, I'm reviewing your paper and you've proposed something, my first question to you is going to be, what do I do with this and what does this mean? Right? So you had better come to me with a path that led to this, that illustrates something. Okay. Actually, incidentally, on that topic, let me just quickly say, this shape you can write down as some probability. So the natural question to ask is, does Hinge loss correspond to some probabilistic model? Right? Is there some probability of y equals x whose negative probability has this shape? Right? And it turns out that you can't do it, that it's not possible. It's in the Kevin Murphy book, and you can actually check, but it just doesn't integrate to bounds. It's just not a distribution. So it's not just a convenient choice, it's just not possible to write this down as a probability. Okay, done that. Okay, so we're going to kernel trick, and before we get to the key intuition for the kernel trick is you write down the dual and you actually realize that I can solve the dual in the same amount of time regardless of what feature map I use, if I just do something called the kernel trick. And for that, we'll need to write down, we need to understand Lagrangian duality. So I sent you the video to look at. Hopefully everybody's done it. So let me just skip to that slide. No. But let me actually get to Lagrangian duality, and what I'll try to do is I'll try to refresh it, and I'll try to write down the dual of an SVM, which will be interesting. Okay. Before I write this down, let me just say that so what I'm writing down is now comfortably beyond the scope of machine learning. Right? This is what you're exposed to in a convex optimization class. So, for example, I will never ask you in any exam to do Lagrangian duality, right? Which is good, which means you can sort of relax, sit back, things make sense, good. If not, it's just half an hour or 15 minutes. Right? But the reason why I'm doing it is the reason why I'm doing it is because it exposes it's an extremely fundamental tool that shows up in a number of areas and a number of problems of machine learning and outside. And it exposes a particular structure that is utilized in a lot of different problems. And it builds character. It's a good thing to do. Okay? Alright, so our goal is going to be, we're going to write down some canonical optimization problem. You're trying to minimize something in W such that G of W is less than or equal to 0, H of W is equal to 0. Why minimize, why not maximize? Just a choice, right? It's just a notation. Everything will be swapped if I don't turn on the maximization problem, and I remember for minimization, so that's why. Boyd chose minimization, and then we're stuck. Why less than equal to thing? Again, just a convenient choice. If you actually have a greater than equal to, just replace G by minus G, and then you're done. So the special cases are going to be there are some inequality constraints and there are some equality constraints, right? And there's some objective function. We haven't even said convex, anything, we haven't placed any restrictions on any of this. And what you'd like to do is, you'd like to solve this problem. The thing that we're going to do is we're going to introduce an object. And that object is going to be a function. It's going to be something called the Lagrangian function. And what we're going to do is we're going to introduce something called a Lagrangian multiplier, or a dual variable. Right? It's known by multiple names. And one for every constraint in your original problem. The interpretation of this I'll explain in a second, but the way to think about it is, this is, why would you ever need to know this theory? You have some problem, that problem seems hard. Those constraints seem difficult. You wish those constraints didn't exist. Or those constraints existed, or this thing existed in the objective. That would be nice. And that's when you'd like to look at the Lagrangian function of the dual. Right? So here's what the Lagrangian does. You write down f of w plus alpha of g of w plus beta of h of w. There's going to be a constraint that the Lagrangian multiplier or the variable corresponding to the inequality be positive, and there's actually no constraint on the Lagrangian multiplier corresponding to the equality. Right? And we've written down some functions. So far, I haven't told you what is this, why are we doing this. Right? Actually, immediately as you write down, there's something that jumps at you. That if these things are actually true, right, if everything I've written down, that if W is, for example, feasible, if W satisfies this thing, then this term is unnecessary, it's just 0. This term is negative, this term is positive. So you end up with a number that is objective minus a negative value. Right? So it gives you a lower bound on this immediately. Right? So for feasible W, by feasible W, primal feasible W, so this is the optimization problem. Feasible means that W satisfies this. The Lagrangian gives you a lower bound on the objective function value. That makes sense? Okay. The way to think, there are many interpretations of the Lagrangian. There's some in economics and other fields. The one that I like the most is a game theoretic interpretation. You should think of two players. One is the primal player that controls W. So this is player 1. And there's another player, which is the dual player, which controls the dual variables. Think of this Lagrangian, this number, this is a scalar, right? These are some knobs. These are choices that the player 1 and player 2 make. For those choices, this scalar is a payoff from player 1 to player 2. It's a zero-sum game. You make some choices, I make some choices. Whatever is this cost gets paid from player 1 to player 2. So player 1 wants this to be a small number. Player 2 wants this to be a large one. It's payoff. Okay. So player 1 wants to minimize, player 2 wants to maximize. Right? There are two ways to go in a game. You can let player 1 go first, or you can let player 2 go first. So there are two games that you can play. And there's, in that order, two optimization problems that can happen. Right? So you can do max over alpha greater than 0, comma beta of Lagrangian W alpha beta of min over W. Or you can do max first, alpha greater than 0, beta min of W.
So why do we want to maximize? What's the point for maximization?
So far, I'm just setting up, like I'm the rule keeper, right? I'm setting up a game. Why does this player want to maximize? Because L reflects a payoff. It's a payoff from player 1 to player 2. Player 2 wants high payoff, player 1 wants to pay less. So that's why player 1 wants to maximize, player 2 wants to minimize. And there's two ways to go in the game. Right? Yes?
Alpha is greater or equal to 0 and then beta under, what is that notation?
It means, so anytime there's a min or a max, anything I write under that, it means those are the variables I'm taking a min or max over, and I've actually just embedded a constraint in that.
Okay.
Right? There is no constraint on W. In fact, these are constraints that we'd like to get rid of. Right? These were difficult constraints, if you will. These are simple constraints. Just positivity is not bad. So there's no constraint on W, alpha is 2 positive. And it should be clear that I've written one constraint, but it would be many equality constraints. It would just mean there would be an alpha 1, alpha 2, alpha 3, there would be a beta 1, beta 2, beta 3, and there would be more terms here. Right? Yes?
So basically, and then on the left one is the player 2 playing first, and then
Right.
the right side, okay.
Yeah. So two ways of going. You can let player 1 go first, then player 2, player 2 go first, then player 1. Okay. And it'll actually turn out that, so this is the same value. You do, so pop quiz, min of max or max of min? Sorry, I haven't finished the question. What was the answer? Sorry, what was the answer again? min of max or max of min, what I was going to ask is which one will be smaller? That's the question.
Max min.
Max min will be smaller. Why?
What if you have a constant?
What?
What if you have a constant?
If you have a constant, then they're both equal. I'm just asking which one, like, is there a greater than equality sign somewhere?
Because we've already found the min, so the player that was trying to find the max, he's trying to find the max between the minimum value. So
The
there is
player
nothing
that
that we
goes
can do.
first will do better, yes.
Yeah.
So there's a W and there's an alpha. There are two choices. I'm just writing a matrix. It's sort of this sort of a matrix. That's the payoff function, right? L of W comma alpha. If you take the min over W, right? So for each setting of alpha, if I take a min, this is 0, 0. If I take a max over alpha, this is 1, 1. Clearly max of min is less than min of max. And this is like an extremely fundamental thing, like von Neumann theorem or something. Right? So which way is it? So I'm going to call this value as P star, this value as B star, and we just established that P star is greater than or equal to B star. Does that make sense? Okay. So one quick thing, where are we going with this? What do these things mean? We started off with this, I had one optimization problem, I introduced two more. So let me just make one of them go away. So it turns out that this optimization problem is exactly this optimization problem. Why would that be true? So let's stare at this. You have this maximization over the dual variables of this Lagrangian. And you're trying to minimize this. This is unconstrained minimization. So there are two choices. Either you satisfy the constraints or you don't. Right? There are two sets. You can minimize, so think of, this is the space of all W. I break it down into two halves. One where you satisfy these constraints, one where you don't. When you do satisfy the constraints, we already argued, if you satisfy the constraint, this is 0, this is, yeah, it was negative. So what does the dual player do? Right? So you give it a negative, so think of W, you're the primal player. You've chosen a W where this thing is negative. The dual player wants to maximize. So it does not want this to be a large. So if this is a large positive value, this will become a large negative number. The dual player does not want that. So the dual player chooses alpha equals 0. So you get f of W. And so when the constraints are satisfied, you get f of W. When the constraints are not satisfied, which means either this is a non-zero value or this is positive. If this is a non-zero value, the dual player can take it to infinity. If it's positive by beta positive, it's negative by beta negative. Right? So in either case, when the constraints are not satisfied, that minimization, you can't do better than infinity. Because every time you not satisfied the dual player, he gets to go first, takes it to infinity. Right? So the best thing you can do is stick to the feasible region. Does that make sense? Okay, so this optimization problem, because the objective function here is the same as this objective function, subject to the constraints of satisfiability, it's the same thing as this problem. Okay, so one way of playing the game is what we are interested in. Right? It's the other way that will end up being an interesting thing. The other way of playing the game is the primal player minimizes first, which means you end up, this is a maximization problem in alpha and beta, and you end up giving think of these as penalties. Alpha is a penalty, beta is a penalty for violating that constraint. Right? So the dual player gets to choose the penalty and the primal player gets to do the minimization. Does that make sense? Okay. We have already shown that this is D star, this is P star, so now we know P star is actually the optimization, the optimum of this problem. We know P star is greater than or equal to D star, but it turns out that we actually know something slightly more, that if this is P star, we know that f of w for any feasible w, has to be greater than P star. Okay? There's a minimization problem here, subject to certain constraints. As long as you satisfy the constraints, you cannot do better than the minimization problem, than the optimum. So it's actually this. We know this is greater than B star. And if I call this function L of D of alpha comma beta, it's some dual function. I haven't written down what that dual function is, but this is some function that you're trying to maximize, that the dual players are trying to maximize. That must lie here. So there's this nice hierarchy. Any feasible primal objective function must be larger than the best you can do in the primal, which is larger than the best you can do in the dual, which is larger than any other feasible dual. That makes sense. So even if you haven't solved these optimization problems, even if you don't know what P star D star is, you've just gotten an upper bound and a lower bound relationship. Any primal, there's a lower bound that you can derive from the dual. Okay. So the key thing to ask in any of these problems is when is this, so this is called the duality gap, the difference between the primal and the dual. When you solve the dual, you get an objective function value. Is it going to be equal to the primal value? That's the duality gap. And when is duality gap 0? Turns out that there is a sequence of conditions that are necessary and sufficient under certain conditions. So those conditions are known as KKT conditions. Karush Kuntakar? Kun Karush Takar? Karush Kuntakar? Thank you. So it turned out, I think, if I remember the story correctly, in 1940s or 50s, Kun and Tucker were the ones who did this KKT condition duality stuff, and it turned out it was actually done by one of the other Ks, the Karosh or Kun, one of them, in a 1925 master's thesis. He just hadn't ever published it. They'd done the same thing, and they were kind enough when they discovered that they named the thing KKT, adding an extra name. The moral of the story is not everyone would be that kind. I highly encourage you to publish if you actually have some good ideas. Okay. KKT conditions are about when can we actually say that the duality gap is 0. I'll just write those KKT conditions. We will not prove it. The reason why I'm writing it is because next time we will start with an SVM quadratic program minimization problem. We will write down the dual for an SVM, and that will expose some interesting structure. And we will have to ask, does solving the dual tell me something about the primal? Am I solving the same problem? Right? And those conditions are essentially, there's the really easy conditions that, and so what are we talking about? We're talking about let W star be actually primal opt. It's a P opt. Let alpha star beta star be dual opt. So you go ahead and solve the primal problem, that gives you W star. You go ahead and solve the dual problems. By the way, I'm not a numerical analyst, so I always think of mins and not infs, right? So I'm assuming nicely that a min exists and an argmin exists. If you take a numerical analysis or a convex optimization class, all my mins will be replaced by infs, and like there'll be a bunch of extra subtle conditions. I don't really care about that. But so you have a primal optimal solution, you have a dual optimal solution. KKT conditions say that basically if KKT conditions are true, necessary. If P star is equal to D star, if you have 0 duality gap, then KKT conditions will be true. So P star equals D star will imply KKT conditions, and I'll write them in a second. And the reverse will be true under certain assumptions like convexity and something called status condition that we won't actually get a lot into details of. But the KKT conditions are pretty simple. The simplest one is you have to have dual feasibility. You have to have the fact that alpha star is greater than 0. Right? Can't actually, if you violate that, then this just can't be true. You have to have primal feasibility, which means G of W star has to be less than 0, H of W star has to be equal to 0. That's just prima feasibility. Whatever your solver actually gave you back as an answer better satisfy the feasibility. So that's like vanilla, can't avoid that. The thing that ends up being interesting is that the gradient of the Lagrangian with respect to W at W star, alpha star, beta star is actually equal to 0. So pretty simple first order condition that if you're trying to minimize the gradient better be equal to 0. Right? And then there's the interesting one that alpha star of G of W star is equal to 0. This is something called a complementary slackness condition that in this product, one of these two numbers, or at least one of these two numbers has to be 0 at optimality. And that relationship is going to lead to a particular understanding about SVMs. The reason, the fact that that's true tells us something about SVMs. Okay? Why do we write these things down? Because if you can write this down, so the way you end up using these things is somebody comes to you and says, I want to solve this optimization problem. You hand derive a bunch of KKT conditions. This is an equality constraint, this is an equality constraint, there's, usually these are fine. You solve this either numerically or through a solver that gives you a solution to this. And this is a necessary condition. Right? So in order to be sufficient for strong duality, you need to assume something else, usually convexity and stated condition. But if those are true, then the solution to these will be the strong dual solution. Does that make sense? Okay, so let's stop here. Next time, I won't explain this again. I'll write down an SVM QP and we'll write down the